transistor. And field effect transistor further divided into two parts, junction FET and metal oxide semiconductor MOSFET. And junction FET is further divided in the depletion mode and the N channel and P channel. Same as the metal oxide MOSFET is further divided into the two parts, depletion mode and enhancement mode. In case of the depletion mode, the depletion layer is already created. In the enhancement mode, you just creating the gate voltage, applying the gate voltage and just creating the channel in the form of depletion here. Okay, the further depletion mode, the N channel and P channel further is divided, and the enhancement mode same here. The two types of devices created, N channel and P channel. Now, these are some key points related to the MOSFET affecting the complete technology file and the complete the device structure and the complete behavior of the MOSFET. Basically depend upon the packaging type, voltage gain, gate oxide thickness, noise factor, load resistance, power dissipation, microelectronics application, thermal management. These are some of the random points related to the MOSFET. Now, just see here, this is the complete 3D diagram and the 3D structure of the MOSFET. In the previous slide, we will discuss about the N-type MOSFET and the P-type MOSFET. Basically, depending on the substrate type, you see here, the P-type substrate, the device is the name as a NMOS. Basically, the naming of this device depending on the channel. Basically, in the P-type substrate MOSFET, the channel is creating the N-type channel. In case of the N-type substrate, the channel is creating the P-type. The whole device name is the PMOS. This is basically a three-terminal device, basically a voltage control device. This is a controlled by the gate. The mechanism is the MOSFET mechanism is basically based on the capacitive behavior. You just create a look like a capacitor. Now, basically, this is a simple NMOS MOSFET. Basically, this is a MOSFET structure and the P-type substrate here, the source, and this is gate contact, and this is one is the drain, and this is the laterally cut line, and you just see here the band diagram, E band diagram, and the E band diagram showing here. This one is the source cavity. Basically, in the previous structure you show here, this is the N type, and this one is the N type, this one is the P type. So here, this band diagram, in case of the N type highly doping, the equilibrium layer is closely to the conduction band, and see here the Fermi level is closely to the valence band. And same case here for the drain, that is the highly N-type doped. This is the Fermi level is close to the conduction band. This is the complete E-band diagram of the MOSFET. And now we go to just creating a simple NMOS and PMOS. After that, you goes to the CMOS structure. Basically, CMOS is the complementary FET, basically made up of the one NMOS and one PMOS. You just combine together and just make the CMOS circuit here. Basically, all are the electronic circuitry, like as just making a simple op-amp and just creating a mux and the clipper clamper circuit, gates, and all types of combination of applications based on the CMOS technology. And this is the complete 2D structure and 2D overview of the CMOS transistor, and the CMOS technology is a combination of the two transistors, NMOS and PMOS is shown here. Basically, in the complete substrate, you see here the complete substrate is P-type, and just creating the N well for the PMOS transistor, and just same in the previous design you saw here the both the sides of the N plus doping and N plus doping here for creating the N MOSFET, and the P plus doping is P plus doping for the P MOSFET. We saw here in the single substrate, and the circuit diagram look like this. You see here. Now these are the basic needs of the CMOS circuit, why we use, where we use, and what is the importance of this the CMOS circuit. Basically, depending on the low power and the high noise immunities available in this complete technology, and the scalability is also a very important part of this circuit, and the high density and the cost effectiveness and the high speed here as compared to the other logic gates. And this is basically a lambda based design rules. So basically, and the BTech students, some are don't know about the lambda rule. Basically, this is for MTech and the upper of the MTech classes. Basically, the lambda rule based on the designing a layout part. Basically, in case of only single device designing, you just create only a single device test on a fab, and you just creating single device on a TCAT tool or any other TCAT tool. You just create only a single device. And when we goes to a chip or a multiple device like a microprocessor, microcontroller, and other type of processors, you just go to the layout part. Any foundry just take the layout GDS file, basically graphical design interface file, and you just take it and you just create the complete processor and complete microcontroller devices fabricated on a single silicon wafer. So basically this is a very important part of this future technology and the current ongoing technology for creating a multiple device on a single chip. This one is showing